Hi, my name is Lee Jasper, and I'm going to be talking about VPM and our experience with it, especially during operations. This is a AFRL small satellite portfolio mission, and I'd like to, of course, thank all my co-authors who had generally way more input and work on this mission than I, either through the design and integration phases, as well as operations and even data processing that we're doing today. Great. So VPM is actually the VLF propagation mapper, and it's working in conjunction with the DSX AFRL spacecraft that emits VLF signals, and VPM will measure it in a different orbital regime. And what's cool about this is we can see natural and man-made signals and watch how they propagate. The technology aspects that we were actually looking at for this mission as well, that not just the science portion of the mission, was evaluating commercial C3 networks as well as the commercial spacecraft bus and how well they would work for an AFRL or an Air Force mission. The payload was just a dual channel VLF receiver, magnetic as well as electric field measurements, and we went into an orbit basically just above the space station. Okay, so I'm going to talk a little bit about how we set up the program, a couple design decisions, and then get into how well that worked out for us. So the overall program kickoff, what we did was define the scope and the overall priority of what we wanted to have happen and when. And if there's more time, these are the extra things that we could do. And so with this definition and clearly defined scope, minimum viable product is maybe a word you could use, we understood what the team needed to do, and this allows us to delegate authority, and this is very important in the small satellite portfolio. We're constantly trying to delegate authority and push it down to the teams implementing the missions, and what this allows them to do is, if they understand the scope and prioritization, they can make their own decisions well within line for what's desired. And this allows them to essentially assess the impacts of decisions they're making. And we can place trust in the fact that if something's about to break, they can elevate that outside of the mission and say, hey, we need help here. So what delegating authority then allows us to do is really execute missions, what we hope is on a faster timeline. And we accept a bit more risk. But generally we can design things and move a little bit faster. And that then, in our design approach, especially for VPM, we said, hey, we know we're going to have iteration here. This is just part of this mission and what we're going to be doing. And so the iterative prototyping is something that was expected, anticipated, and allowed without really a whole lot of extra insight and oversight and discussion. We just let the team roll. So in design and integration, using that program setup, we then also with the team sort of said, all right, there are two big things we want to do here. So we're leveraging COTS components, but what that means is they have a variety of interfaces that may or may not work very well together. So the team was directly responsible for creating these custom interface cards that we would use. And this allowed a level of configurability and responsiveness in the electrical, as well as elements of the mechanical design. The other side of that then is, and this is reasonably heavy lift, but one we found very important, was the flight software will also be done in-house. And doing the flight software in-house essentially allowed us to get the behavior out of the system that we wanted, right? Not only could we integrate the system together as we wanted, but now the flight software gives us the actual behavior and hopefully performance we were expecting. And a lot of that was done through encapsulated functionality, modular design, and thinking through how we want to make sure things are reconfigurable. And so if hardware item or whatever, the interface was not very well understood by us, and as we learned as we integrated and prototyped with it, oh, this interface is different. The flight software, we only had to change a small portion and the rest remained the same. We didn't have any sort of this weird trickle down effects or anything like that because of good modular design and encapsulation. And I'll talk a little bit about how that helped us again. But these two key decisions were highly enabling. Now, the other thing that we do, and this is kind of a theme throughout the rest of the presentation, was in the smallsat portfolio, we have this concept that you should design for a tumble because the philosophy is that probably all small satellites tumble at some point in their life. And so what that really yields is kind of these three major bullet points on the slide that drive elements of our design. The first of which is spacecraft power systems. We generally want to generate power throughout the tumble and also have safe operational modes that we could utilize even if we're uncontrolled. And so what we do is actually fairly standard for a lot of systems is kind of have this degraded type state of nominal all the way down to a Phoenix mode, which at the bottom end with Phoenix is really the vehicle is off, but we can still trickle charge the batteries and eventually reboot once their state of charge gets high enough. And so we kind of have this, we can work well all the way down to we're not working, but we have a mode of recovery. All of those things are sort of built in to the system. The next thing is really ideally, you can get information out of your system even if you're not sure where it is. And this is highly important, especially at the very beginning when you get deployed. The TLE is fairly coarse, so you're not exactly sure how to point your ground antennas. One way we get around this is using Globalstar, which doesn't rely on really any knowledge of position. It can just transmit and hopefully you receive small packets. And then, of course, radio uplinks, we want to be able to, and downlinks for that matter, close them when you're tumbling. And this, again, is utilized, maybe not as much in smallsat, but many spacecraft use near omni antenna coverage for the line of sight radio. And so we had VPM designed this way as well. So, great. We have all of this, these kind of big things designing for a tumble, but we're going to be sporty and we're going to aim for success. And we said, let's have an automatic deployment ConOps where we come out of the canister, deploy panels, detumble, and we're going to point right at that sun and be power ready and maybe do all of this before we even hear from it. As you might see over here, this is not necessarily how it went. So I'll get into that. All right, operations. So VPM launched on December 5th and actually launched on a SpaceX rocket. And this is kind of cool. It got carried through the space station by astronauts, as you can see, and was attached to the end of the Cygnus, which eventually undocked, boosted, and kicked out a bunch of secondaries. We were one of them. So we've been handled. VPM was actually handled by astronauts, lived on the space station for a while. It's kind of cool. But, right, we had this great idea, like, let's come out. And we're going to be perfect, and we're going to point at that sun. But we were one AI in tissue away from achieving that plan. And yes, I'm poking a little bit of fun at a guy who probably never will see this presentation. But either way, poor Michael, it wasn't really his fault. But someone has to be the stucky. So I'll describe what happened there in the next slide or two. So February 1, we get deployed. We got our first Globalstar beacons fairly quickly. And they demonstrated, or they showed that solar panel deployment had occurred, but we weren't really detumbling, and it looked like we were power negative. So this little flow on the side of the chart here, we had nominal all the way degrading down as battery state of charge went down into Phoenix mode, and eventually, once we trickle charged, we would reboot into sun safe mode. Over the next 10 days, we essentially went through the cycle multiple times and rebooted more than 50 times. So we were in a pretty rough state. And one of the initial things we did after the first few days was we realized we just need to stay on longer to hopefully increase the chance that we'll catch the vehicle while it's on in a pass. And so with some of the software configurability that we were able to utilize well in operations beyond AI&T is quickly change our boot mode from sunsafe to survival, and that gave us a lower power consumption and higher likelihood we could hear from it. Great, so we did all that, and VPM started to get some help as well. As not only did we get this lower power draw, but we had increasing illumination overall, and we started to just understand where the heck VPM was better. And so we got greater command and data authority, and that then allowed us to get this plot, which I kind of loved. So we had suspected the magnetometer maybe was an issue. And so what this plot shows is the first 7 seconds is the primary magnetometer measurement and what we expected the range to be, those top black dotted line. and the remaining time is the secondary magnetometer that we let measure. And what you can see is essentially it should be falling roughly in that purple bar, but the primary magnetometer is clearly dipping well outside of the overall estimated magnitude versus the secondary magnetometer basically fits right in. And this is really cool because this is the smoking gun that, yes, in fact, the magnetometer was screwed up, which is what we were using to do our B dot detumble mode, and thus why we were not detumbling. So the magnetometer in the end was plugged in incorrectly during AINT, and we at the time only knew that it was a sun sensor, and so we did all our due diligence to make sure the sun sensor was appropriately tested after we had that reverse mounting configuration. But because we didn't understand there was a magnetometer in this package as well, we had never actually tested for that and flew something that had been broken. The nice thing is obviously the vehicle was resilient enough to stay with us while we figured out what we had done. And in the end, we were actually able to recover from this tumble. We swapped the secondary magnetometer, again, another flight software configuration and reconfigurability that was just built in that made this process not particularly challenging, right? It could have been a lot worse. And this was done, again, this whole process in about 10 days. We were detumbled from about 40 degrees per second to 3-axis pointing towards the sun in about 16 hours. And ever since then, the vehicle, with respect to all of these challenges, has done quite well. So that was a really cool debugging thing. And so we were so close in AINT. So, but the question is, we have this design thought and concept, right? Does designing for a tumble work? So I think the answer is yes, but we've caveated that a little bit. So do all small sats tumble? Maybe not all. We can't prove that with VPM, but certainly VPM did. And boy, did it tumble. We had some pretty high rates, as best as we can tell. But if we move on from that, generating power and operating in a safe mode. So obviously we have these degraded modes based upon battery state of charge. But on top of that, we actually go a little bit further and allow our lowest on mode survival to actually include no attitude control and therefore allow a tumble. I'd say this is a bit more uncommon, but it enabled us to have longer periods of time and chances to actually talk with the vehicle. And this type of risk acceptance and degradation in functionality actually was very enabling to us debugging this problem. All right, generating power. VPM actually is pretty cool, but unfortunately it only generates power on essentially one hemisphere. And we're sort of thinking through that because in the end it worked for VPM, but we still had plenty of times when we totally discharged. And so we're thinking through how only a single hemisphere generation, how good that really is. Okay, receiving telemetry when you don't know where you are. Global Star Beacon. This worked super well. We had aliveness, key state of health information, and this plot here shows over the last few months, every red dot is where we received a full beacon. And you can see we get it basically everywhere all over the Earth and reasonably consistently. Even at a 30% success rate in aggregate, it sufficiently enhances our ability to understand the state of the vehicle and plan for our operations, even without a line of sight connection. So this has been incredibly enabling. All right, radio uplinks. So we have an omnidirectional antenna or set of antennas. It works really well. This is a standard feature and should happen. Okay, so left out a ton of stuff from the paper, just kind of focusing in on a little bit of this ops recovery as well as how does designing for a tumble work. But we talk a bit more about design activities, flight software environment, and all those things. So there's quite a bit more discussion of the overall system in the paper. But one thing I wanted to point out is that this is, as best as we understand it, the first time the Air Force has owned and operated a vehicle that has used commercial ground service providers and cloud-based data system for the operations and remotely operated the spacecraft. And this was kind of forced upon us by COVID, but the team was able to quickly adjust and really had fairly limited problems, even though we were able to maintain social distancing and everything. So a very cool output from COVID. All right, and I'm out of time, but yeah, we think you can build resilient systems, and surviving a tumble is one of the key ways to do that.